components of the network are the internet service provider's equipment, which belongs to the internet service providers and we don't have control over it. So major components which belong to the internet service providers are ISP's equipment, routers connected by transmission lines, this is what we have in the oval here. In this shaded oval, this is the internet service provider's equipment. So we have routers, and the circles A, B, C, D are routers, and the lines are transmission lines which connect the routers together. And then we have other equipment, which is the customer's equipment, is outside of the oval. So let's say the host A is a customer which wants to send a packet to host B. So these are in some, let's say, private homes. So they do not belong to the internet service provider. They're outside of the oval. So store and forward packet switching means the packet will be sent to the nearest router. When the router receives that packet, it will store the packets shortly. It will examine the packets. It means it will calculate the checksums and verify that there are no problems with the packet. And so it stores it, briefly stores, and next forwards it to the nearest router. The next router is going to do the same thing. It will take the packet, it will store it briefly, examine it, forward it to the next router along the path to the destination until it reaches the destination. Track packet is transmitted to the nearest router. Router stores. Stores the packet briefly, it examines it, checks the checksums, and it forwards it to the next router along the path. when we are designing the algorithms in this layer, we need to consider, we have several considerations to make. The first is that whatever we do, whatever we design, it should not be dependent on some particular router technology. So if any of these routers are removed or replaced, that should not affect the functions of our algorithm. The layer above it should not be concerned with the types of routers that we have, how many routers that we have, how they are situated in terms of topology, their geographical locations or anything like that, which means if any router is removed or moved to another place or changed to a different new type of router technology, that should not affect our algorithm, and the layer above it should not be affected or concerned with that. The next thing is that we need to have addresses in this layer. So in order to connect all these machines anywhere in the world and be able to send packets from a sender to receiver, we need some unique identification of all the machines that will be part of the network. In this layer, we provide these unique addresses. So these addresses that we choose and the way that we design them has to be uniform along the whole network. It means all the networks in the world that we have. So it's a uniform numbering plan. That's what we mean by that. Now, we mentioned we can provide two types of services. The most common one, which exists and is in use in practice today, is the connectionless service, which we also call a datagram. And we call it a datagram in analogy with the telegram in a post office. The telegram is sent once, and whether it's received or it's not received, it's a one-time thing. There is no confirmation, there is no tracking, there's no sequencing, there's nothing like that. So it's a best effort delivery system. So there is no connection, it's fast. You send the telegram, boom, it's received. But there's no guarantee. Maybe you'll make it, maybe not. There's no confirmation of any kind. That's why we call it a datagram, because we are using that same idea here. When we don't have a connection in the network layer, we are doing a best effort service. We're gonna send these datagrams or packets, and if it makes it there, it makes it. If not, then it didn't make it. We don't provide any guarantees, but that's fast. And it's fast exactly because we don't have to track all these things and receive acknowledgements and insurance of some sort. They arrive, because that's going to slow us down and create overhead. So let's look at the connectionless service that we have here.
This table is routing table?
Yes, that's a routing table. Okay, so the host, the process, this is the application. The process is the application which is sending some message. Has a very long message to send. The message is 4 times longer than the maximum transfer units. which means the network layer has to break this message into 4 pieces in order to pass through the network. Every router, as you have seen here, already noticed, every router has internal routing table. This routing table, what it does, it specifies where to forward a packet, and by where we mean on which interface to forward an incoming packet. So for every outgoing line, we have an entry in the routing table. So for destination B, we will send on line B, because B is directly connected to A. So this is the routing table for router A. Destination B sent on router B. What we have listed here are the line is the network interface card for each network on which the router is connected, or on which the router is on. So router A is connected to router B and C. These are his or its neighbors. So he can either send to B or to C. There's no other choices here. So if the destination is B, it will send to B. If the destination is C, it will send to C. But there could be other destinations. So let's say D. To get to D, it's gonna go through B. Why it's gonna go through B? Because that's a decision that the router has made. That in order to get to D, the shortest path and the best way to go is to B. And we record this in the routing table. To get to E, we're gonna go through C. Because let's say C, that's the closest path. Or there is a shortest delay, or it's using some other metric to decide that it should go through C in order to get to E. And then for F, go through C. So every router has a table like that, which is specifying where to forward a packet for each possible destination. Only directly connected lines are used. So, by following the information in the table, each packet is forwarded on the appropriate line. So the host 1 has a long message to send to host 2. The message network layer has to break it to 4 parts. In the first part, so it's going to F, from A to F, the destination is F, because that's the router which is closest to the receiving machine. That's the last router. So the A looked in its table and said to get to F, send to router C. Then Router C got the packet, inspected it, looked in its table. To get to F, send it to E. So it sends it to E. E looked in its table, destinations F. To get to F, send to F. So the packet 1 got to F, and now the second packet followed the same route. The third packet followed the same route. But something happened to the fourth packet, and it went the other way. Why would it do something like that?
So maybe like between A and C is easy. That's why it selected A, B.
Okay, so one student is saying maybe this path became busy. Maybe there's a congestion on this path, or maybe this router was destroyed. Maybe there was a nuclear war, or it was somebody stole it, or it just hacked and it's dead and crashed. I don't know. This router disappeared. So what's gonna happen? So every once in a while, every particular time interval, all the routers will send information about their neighbors. So let's say they're gonna ping their neighbors, see if the neighbors respond and how long does it take them to respond. And they're gonna send this information to everyone else. So the routers will update their routing tables. So let's say the router A learned from its neighbors that this C router is no longer there, or that this path is taking now a long time, and updated its routing table and saying to go to F, you're gonna go the other way. So now it says to go to F, send it to D. So the packet number 4 went the other way. This really here should be saying B and not D, because D is not directly connected to A. But it updated its routing table that says it should go the other way. So this is for connectionless service. Now we can also provide a connection-oriented service